Now let's use the equation we just derived to discuss something that I like to call a ladder diagram of energy levels. And we're going to be looking at the ladder energy for n equals 1, 3, and infinity, and we'll talk about what these mean, in kilojoules per mole. And because there are no absolute values in energy, we will define zero energy state as when n equals infinity. And there's one other detail. So we have to say which one electron system we're using for this. And the one electron system we're going to use is a hydrogen atom. So this is for a hydrogen atom. And what we'll see, and let me just sketch the idea of a ladder diagram. So if we draw a line with an arrow pointing up, and we think about energy as increasing as we go up the page, then what we should see is that, first off, we'll define n equals infinity as one rung on our ladder, and that will be 0 kilojoules per mole. That's what the zero energy state is. And what we will see is that as the electron goes closer to the nucleus, all the way down, and we can continue this arrow down a little bit more to n equals 1. N equals 1 is the lowest energy state possible for an electron in the hydrogen atom, and in any atom, by the way. And that's going to be the one closest to the nucleus. And from there, though, there's going to be intermediate energy states when the electron is in n equals 3 that we're going to solve for in this problem. But according to the equations and according to quantum mechanics, n can have any value. So 2, 3, 4, 5, and as n increases, just like the Bohr model would say, the energy increases and you get farther from the nucleus as well. So let's see what this looks like now. So from previous page, we have this equation. E equals minus 2.18 times 10 to the minus 18. Those are joules times z squared times 1 minus nf squared. Sorry, 1 over nf squared minus 1 over ni squared. And what we're going to do is we're going to define, at least for our calculations, that ni will always equal infinity. And that means that we're always thinking of our electron from starting in a state that's n equals infinity. And let's talk about that. When n equals infinity, if this is the nucleus of the atom, this is the tip of my finger, and the tip of the pen is the electron and its average distance from the nucleus, then n equals 1 is here. As we move farther away, we get to n equals 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And n equals infinity is when the electron has left the atom. And we're not saying where it's going. All we're saying is it is no longer associated with the atom. And functionally speaking, it is at a no longer interacting with the nucleus in any way. So ni equals infinity. That's going to be our starting point. What does that mean? When n equals infinity, it means that the electron has left the atom. So n equals infinity, and let me change back to, there we go. N equals infinity means that the electron has left the atom. Is no longer interacting with the atom, that is. Okay, so that will, as we have now this term where it's 1 over infinity squared. Well, 1 over infinity is 0. 1 over infinity squared is also 0. And that means that if we start here and we think about the energy going down, we can eliminate this second term, and we're left with E equals minus 2.18 times 10 to the minus 18 joules. Z equals 1 for hydrogen. Z equals 1 for hydrogen. So this just becomes 1 squared. And then we're left with 1 over n final squared. And again, this is one number, but it's always indicating that we're starting at n equals infinity and thinking of the energy change as the electron moves closer to the nucleus. And so let's do n final equals 1. For that, it's going to be 1 over 1 squared, which is still just 1, times 1, times minus 2.18 times 10 to the minus 18 joules. So the energy is just minus 2.18 times 10 to the minus 18 joules. That is our energy. And like similar calculations we've done before, this is the energy of one electron moving from n equals infinity to n equals 1. So energy of one electron moving from n equals infinity to n equals 1 in hydrogen. And I'm leaving this space down here open because I'm going to write some stuff. When we're moving from, let's call it Ni equals infinity to Nf equals 1. Okay? And because it's the energy of one electron, we can do per electron similarly to what we've done for per photon before. And in fact, when this electron moves closer to the nucleus and gives off this energy is negative, which means this energy is given off. This is an exothermic process. Typically, the atom and the movement of the electron in the atom gives off energy in the form of light. And so you'll also see joules per photon because the photon will be given off as this process occurs. We'll talk more about that. Okay, so now we have joules per electron moved in the atom. Now we need kilojoules per mole. So let's do this process. So we have joules per electron, and minus 2.18. We'll expand it to be joules per 1 electron. That's the same thing, but longer line. And now we will change joules to kilojoules, 1,000 joules is 1 kilojoule, and 6.022 times 10 to the 23rd electrons is 1 mole of electrons. And if we multiply this out, so 2.18 minus exponent 18 minus divided by 1,000 times 6.022 times 10 to the 23rd. I get minus 1,313 kilojoules per mole. And that is the energy in going from 0 here at n equals infinity, or 0 energy, down. So I'll draw an arrow going down. The energy difference is minus 1313 kilojoules per mole. And since this is 0, if you then go down minus 1313 kilojoules per mole, you get to negative 1313 kilojoules per mole. And we have done just n equals 1 so far. Now let's do n equals 3 and final equals 3. We'll do that in red. This time it's going to be 1 over 3 squared, or 1/9 of this number. So let's go ahead and plug that in. 2.18 minus exponent 18 minus. Still got the 1 squared, which is still 1, and we don't have to do the math there. Then, so 1 over 3 squared, or 1 over 9. So just divide it by 9. I get 2.42 times 10 to the minus 19 joules per electron. Well, joules is the calculation there. Then it's for 1 electron moving. So we put in the joules per electron. Run through this process again, divide by 1,000 times Avogadro's number. And I'll go back to, oh, don't forget your minus sign. 2.42 minus exponent 19 minus, divided by 1,000 times 6.022 exponent 23rd, minus 146, let's say, 146 kilojoules per mole. And let me slide over here. Again, this is for the process of starting at n equals infinity and going down 146. And that is the n equals 3 line. And that will be minus 146 kilojoules per mole. And I've gone down about I think a tenth or so, since it's about a tenth of the distance down here. And if we were to go, let's see, so that covers 3. And so our ladder looks like this. Here are the 3 rungs. 0, 3, n equals 1 is way down here. You could use the calculation here for 1 and 3, and you would get the difference between 1 and 3 here. So about, I don't know, about 1,100 plus or minus kilojoules per mole difference there. The equation is totally useful. What you would see, though, is that the spacing of the rungs in terms of energy depends on 1 over the square of the number. So each rung on the ladder gets squared closer and closer to each other each time. If we were to try and approximate the n equals 2 value in here, it would be somewhere there. So the difference between 1 and 2, n equals 1 and n equals 2, is a big jump, and then each successive jump gets smaller and smaller until we get to n equals infinity.